a logical structure composed of predicates, or tests on conditions in the world, actions, which EVAR can execute via effector commands, and goals, which define the tasks that need to be achieved. Here, the predicate, coupled, asks if EVAR is holding the object, referred to as an astronaut from herein, not tumbling, checks EVAR's spin, and at SSF determines if EVAR is within arm's reach of the space station. When these conditions are satisfied, EVAR can apply the action, open clamp, in order to deliver the astronaut. Note that all three preconditions have to be met before the open clamp action can be applied, indicated by a semicircle underneath achieve delivered. However, they must also be accomplished in left to right order, as indicated by the less than sign. Actions may or may not achieve the goal they are attached to in the plan. If all goes well, and the environment is cooperative, open clamp will achieve delivered, and the value of the predicate delivered will change from false to true. Similarly, close clamp will change the world so that the predicate coupled, which is implemented as a test on sensor data, evaluates to true. Since goals always have the same name as the predicates above them, we omit goal names from later diagrams. The plan is interpreted in a top-down left-to-right fashion, working from the overall goal through predicates to sub-goals. A novel feature is that the interpreter operates in an endless loop, starting from the top each decision cycle. This produces a repetitive game of 20 questions. EVAR diagnoses the situation by testing predicates, finds its location in the plan, and then applies the relevant action. This loop is responsible for many of the system's adaptive properties. We illustrate interpretation of the plan diagram using a retrieval sequence that begins just before EVAR grapples with the astronaut. The system starts by asking if the object is already delivered. If it is false, shown by a red arc, the system begins work on the sub-goal, achieve delivered. It does this by considering the leftmost predicate, coupled. In this example, delivered and coupled are both false, so execution proceeds to the sub-goal, achieve coupled, the details of which are not shown. This series of questions is applied repetitively as EVAR diagnoses the situation in order to retrieve the appropriate action. Once EVAR finishes its approach to the astronaut, it applies the close clamp action to achieve coupled. The moment it does this, the condition coupled becomes true, shown by a green arc in the animation, and the interpreter takes up the next question, not tumbling. Not tumbling is false. The EVAR astronaut pair have spin, so the system moves on to the goal, achieve not tumbling, which is primitive. It has no preconditions. EVAR immediately applies the action, set attitude hold, which instructs the MMU to cancel all rotation about EVAR's center of mass. Since it takes some time for this action to produce the desired effect, the interpreter repetitively selects set attitude hold. After rotation is canceled, the condition not tumbling becomes true. Since coupled is still true, the plan proceeds to test the condition at SSF. Since EVAR is not at the space station, it moves towards it, as directed by actions within the achieve at SSF goal not shown. In order to show how the interpreter responds to interventions, we need to look at a more complete representation of the plan. Here, we expand achieve coupled into three parts. Roughly facing ensures that the object is within 30 degrees of straight ahead. At object demands that EVAR is within arm's reach of the astronaut, and clamp open insists that the clamp is open before EVAR can make a grappling attempt by applying close clamp. The goal for at object decomposes into two sub-goals for facing the object and achieving a standoff position. The first concerns very fine-grained control, plus or minus 5 degrees, while the second in fact causes rendezvous. it instructs EVAR to establish a position 6 feet from the object with 0 velocity, regardless of initial conditions. The action, translate to position, performs the orbital dynamics calculations required to implement rendezvous. EVAR will only move to contact after it achieves this careful positioning. The cyclical interpretation of the plan diagram allows EVAR to respond to interventions. Here, Murphy causes EVAR to drop the astronaut while returning to the space station. EVAR detects that the predicate coupled is now false. Remember that the interpreter processes predicates from left to right. Roughly facing remains true. Since at object is false and facing is true, EVAR adapts by translating to position. When EVAR has obtained the designated position, it moves to contact, and then opens the clamp to complete preparations for grappling. Once all preconditions of the clamping action are achieved, EVAR applies close clamp. Coupled then becomes true. On the next cycle, EVAR tests the tumbling status and discovers that there is no new momentum. The robot begins to return back to the space station, recreating the original state. We can also run the same scenario backwards, modeling a serendipitous event. Here, we imagine the astronaut grabs EVAR before EVAR has completed its move to contact. As a result of this intervention, the robot finds that coupled and not tumbling are both true, so EVAR simply continues en route to the space station. The system does not insist on carrying out every step of the plan. The goals for achieve facing and standoff can be achieved in parallel, as indicated by the absence of the less than sign within the arc. As a result, EVAR can respond to interventions that affect both conditions at once. Here, Murphy rotates and moves EVAR further from the astronaut. Facing and standoff both become false, and EVAR simultaneously reorients its body and translates to position. Facing becomes true first, so only the translate action remains. EVAR soon re-establishes the starting conditions. How does EVAR know whether or not it is facing the astronaut? The answer to this possibly inobvious question induces a major structural change to the plan. The issue is that the computation within facing hinges on prerequisite knowledge, specifically the location of the object. We force EVAR to acquire this information by splitting the facing predicate, in fact, all predicates, in two. The new precondition, know whether facing, abbreviated KW facing, drives acquisition of knowledge. KW facing is false if EVAR has not measured the coordinates of the object. The action sense object satisfies the implied goal. The predicate facing retains its previous interpretation. It compares EVAR's orientation in space with the object's location once it is known. How does EVAR go about sensing the object? This answer is obtained from a refinement of the achieve KW facing goal. Here, we introduce a new, split predicate for testing whether the astronaut is in the field of view of the laser scanner. KW in FOV causes EVAR to determine the object's position, while in FOV tests to see if that location is visible to the scanner. If it is not, EVAR acts by pointing the laser. If it happens that the object is not in the plane of the laser gimbal, the rotating platform underneath the laser, EVAR must reorient its body to enable the pointing action. The KW goal associated with this predicate is modeled as always true. That is, no additional knowledge is required in order to determine if the object is laserable. The KW goals cause EVAR to act in order to acquire knowledge. We illustrate this process by returning to the situation just prior to grappling. Here, Murphy intervenes by rotating EVAR. In this situation, EVAR has no direct measurement of the astronaut's location, provided by the sense object action, so the KW facing predicate is false. It does, however, know a previous location so KW in FOV is true. Since the object is not in the field of view and not in the plane of the laser gimbal, EVAR applies the rotate body action. After rotating its body, EVAR points the laser. This brings the astronaut in field of view. EVAR can now look at the astronaut and measure an exact position, generating an answer to the facing predicate, which is false. EVAR rotates its body a second time in order to face the object as opposed to aligning the gimbal. How does EVAR know where to look in order to find the object? This question is answered by the refinement of the Achieve KW in FOV goal. Here, EVAR simply acts on belief. It applies the predict location operation in the plan. Prediction, however, requires a prerequisite. The location of the object must have been known at some earlier time. If no past location is on file, EVAR will conduct a physical search. Returning to the previous scenario, we see that EVAR's orienting behavior was driven by belief, not knowledge. Here, located is true because the system remembers it once saw the astronaut. It predicts the astronaut will be at the location prior to the intervention. EVAR points the scanner at the expected position. What happens when beliefs fail? The answer to this question requires a further expansion of the plan. First, since we are operating on predicted locations, we change the names of the in field of view predicates to location in field of view. Next, we grow a branch in conjunct with the location predicates that tests to see if the object is at the predicted location. If it is not, EVAR has cause to modify its belief.